So we are looking at tan graphs, and we're going to apply the same principles to this tan graph as we did to sine and cosine. We're going to consider the transformations, and then we're going to see how those transformations affect our drawing of a graph. I can't really handle people talking at the same time, though. I know you're not just chatting, but maybe direct questions to me, and everyone will get the same info then, and I can manage what's going on. But I'm going to just unpack the tan graph as an aid to memory for those who have seen it but can't remember it, but also as an introduction to those who haven't seen it, which is what I just learned. So what I've got here is the tan graph with all of its possible transformations. I'm just going to return it back to a standard graph here. And you'll see that the tan graph, like the sine and cosine graph, is cyclical in nature. It repeats itself, but it has this kind of almost like a wavy kind of graph, and it also has asymptotes going along here, like so. And what I'm going to do now is I'm going to restrict the graph to just one cycle, which is from 0 to 2 pi. So just so we can see it for that little bit of the graph there. So that's what it looks like from 0 to 2 pi. Now, what I want to remind you of is how the unit circle effectively works. I'll draw it on my screen so that you can see it and refer to it when you go back. So if you remember, when we draw the unit circle, we've got a circle with a line of length 1. We know that it's cosine theta, sine theta is any old coordinate. That's how we define it. And what I said to you, if you remember, is that tan theta is basically the gradient. Tan theta is sine theta over cosine theta. So effectively, it's the gradient of that line there. So in the first quadrant, left to right, the graph is going up, right? And then in the second quadrant, when we have the line here somewhere, the gradient is going downways. And then in the third quadrant, where tan is positive and sine and cosine are negative, I'm deliberately going to make it a different angle measurement just so you can see it's not just a single line. We've got a positive gradient again. And then in the fourth quadrant, we've got something like this. Sorry about the wobbly line, but we've got a negative gradient again. So we've got a negative gradient, a negative gradient, a positive gradient, and a positive gradient. Stop there for questions. Should know what a gradient is by now. But what I want to sort of show you, and I'm just doing it really, I mean, normally I'd have what I did in my Method 3 classes, I'd have an interactive where we could just change this line manually. But I'll just use the blue one. If we have a look at the gradient here, can you see how the gradient of this blue line is a lot steeper than the black line? And then when we get to pi on 2, the gradient is now not defined, right? Because it's all rise but no run. So with no run, with no x direction, then we're dividing by 0, and dividing by 0 is undefined in mathematics, right? So at pi on 2, we have no gradient. And then when we go to the other side of so that's pi on 2, when we go to the other side, so now I'm here, I know this is a confusing diagram, I'm sorry, it's just nothing else I can do. We've now got a steep gradient, but it's negative, really steep, but it's negative. Then if I go down to here, I've got no rise and a run of 1, that's fine. So that's got a gradient of 0. Okay? And then if I go here, I've got a pretty flat gradient, which is then getting steeper and steeper until I get to here where it's undefined again. That's 3 pi on 2. And then it's really steep, and then it's getting flatter and flatter until it's flat again here at 2 pi. So the gradient is 0 again. So where you see m there for gradient, that's tan. So again, 0, the gradient is 0, but it's growing quickly until it gets to effectively an infinite gradient and then undefined at pi on 2. Then it goes negative and big and goes down here. Let's have a look at the graph and we can see this in action. This is why the graph is what it is. So remember, this is the graph of the gradient. This is the gradient graph. So the graph starts off as 0 in this. So between 0 and pi on 2, that's the first quadrant. So tan starts off at 0 and gets bigger and 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 bigger as it gets closer to pi on 2. Okay, in the unit circle, that's the equivalent of saying that the slope of this line is getting bigger and bigger and bigger and bigger and bigger because it's getting a steeper line. Okay, when it gets to pi on 2, it's not defined, so we have an asymptote there instead. So there's a vertical asymptote at pi on 2 because the gradient is not defined. Tan is not defined at pi on 2. Move to the other side ever so slightly, and we'll have a really huge gradient because it's steep but negative. And so the graph starts off down here somewhere, really big but negative on the other side of pi on 2. And then, as I was saying to you, it's now getting flatter and flatter and flatter until it gets to 3 pi on 2. So flatter and flatter and flatter means that tan theta is getting smaller and smaller and smaller and smaller, and then hits pi at 0. And then after it hits pi at 0, the graph then starts getting steeper and steeper and the graph. The gradient of this unit line, i.e. tan, is getting steeper and steeper and steeper and steeper, which means that the size of tan is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger until it gets to 3 pi on 2. At 3 pi on 2, it's not defined because there's no run. Rise over run, there's no run. So it's undefined again. And then on the other side of 3 pi on 2, we've got a really steep graph but negative, and it's getting flatter and flatter and flatter and flatter. Really steep graph but negative, and it's getting flatter and flatter and flatter and flatter. Okay, when I say flatter, I don't mean this graph is getting flatter. I'm saying the value of tan is getting smaller and smaller and smaller. So flatter here means a lower value for tan. Lower, 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 until it gets to 2 pi, at which point it is 0 again. And then it will just keep on repeating with that pattern. So this is between 0 and 2 pi. Good so far? Okay, point number 2 though. Really, if you look at it, this bit here is repeated here, and this bit here is repeated there. So between 0 and 2 pi, we are actually seeing 2 cycles of tan. So that means that tan is different from sine and cosine in that it only has a period of pi. Okay, so it's got half the period. So what does that mean? That means that when we're working out the period, we are going to go pi on n instead of 2 pi on n. Okay, pi on n instead of 2 pi on n. So when working out the period, you are always putting the main period size on top, and you're dividing it by n. But I'll look at those transformations a bit more thoroughly, but quickly, team. I want to get this done before the end of the lesson. Because we're newer than I thought, I'll just start with this and then I'll come back. So you can see here this base graph has effectively, if we were drawing it for one cycle, we just need to draw an asymptote at pi on 2, and then we draw a line from 0 up, and then we draw a line from infinity, effectively, to pi. So the bit that I've highlighted in green here is one cycle, it's one period. But because 0 to 2 pi is so common, I've gone all the way to 2 pi so that you can see we've got another repeat here. You can see that we've got our first asymptote at pi on 2, and then the next asymptote is at 3 pi on 2. So the length between these two is pi, which kind of makes sense because that is our period length, right? So if we've got an asymptote at pi on 2, the next asymptote's got to be another pi length along, which is at 3 pi on 2. It also makes sense in terms of the unit circle. We're going to get an undefined value every single every single y-axis, really, basically. Okay, so I need to talk about transformations now. So you need to be okay with what I've covered so far before I do so. So ask questions now. That's a warning. Transformations. As usual, we look at dilations, reflections, and translations, doing them in order this time. Now, first of all, we've got this sense of A. So the value in front of tan, and I've got an absolute value sign there as well. A stretches or compresses the graph just like any other function. We don't technically call the value of A the amplitude. Tan doesn't really have an amplitude. You may find other mathematicians that disagree and would call it an amplitude. I wouldn't, though, because the graph goes on forever in either direction, so there's no maximum minimum from an amplitude. But if we see this in action here, here is A. If I make it big, can you see it's basically just stretching it away from the x-axis? So it's stretching parallel to the y-axis. Or if I make A a fraction, it's squishing it towards the x-axis. In other words, it's compressing or dilating to in the same direction as the y-axis. Okay, that's kind of the effect. In terms of graphing, you can't really do much to demonstrate that that dilation is doing something there. Any questions on that? Okay, I do want to move fast. So N, if you remember, oh man, if you remember, N is the horizontal dilation, and for sine and cosine, it affects the period. Real good? Questions? No. It affects the period in exactly the same way for sine and cosine, as the same way as it differs sine and cosine, i.e. we divide pi, not 2 pi, by n, and that'll give us the new period. So if we have a look at it, I might need to put a few more, I'll just expand it to a forever graph instead of just a limited one, so you can see it in action. So here's our graph going here with our asymptotes at pi on 2 here, and then back by a pi and forward by a pi, and the next one's a pi along and so on. So there's our asymptotes. Just watch those asymptotes as I change n. I'm going to increase n, say to 2. And we can see now that our asymptotes are now squished. So they were at pi on 2, now it's at pi on 4. And then the next asymptote is now pi on 2 length onwards, pi on 2 length onwards, pi on 2 length onwards, because the period of the graph has been squished to pi on 2. And similarly, if I make n equal to 0.5, we are going to stretch out the graph. And so instead of having an asymptote at pi on 2, it is now stretched out to pi. And then instead of the next one being at 2 pi or one more pi on, it's 2 more pi on. So 2 more pi from pi is 3 pi. 2 more pi from 2 more pi backwards gets me to negative pi, and so on. So that stretches the graph, and if n equals 2, that compresses the graph. Okay, that is how dilations work. The main thing is working out that period. Any questions? Okay, translations. Translations, we've either got a vertical translation, which is the plus c here, or we've got a horizontal translation. The horizontal translation is exactly the same as it works in sine and cosine. It's a phase shift. So again, just tackling one at a time. If I make c bigger here, I'll just go to c equals 2. And have I got a stretch factor here? Have I? Yeah. Can you sort of see? I'll just do it again. Watch the center of the graph. So the center of the graph is at pi here. Watch that center. As I go c equals 2, oops. Can you see now that the center is 2 units above? So if you kind of think of this as a center point here, it's the centers that have been increased up by c. Just like the sine graph, really. We look at the center and we reorient our graph based on the center. Okay, so that's that. Bring that back to 0 so we're not confusing things. And again, for B is a translation. So if I go just pi on, I think that's pi on 4, I'll go negative. Negative pi on 4, just keeping an eye on that center. That center is now, is that pi on 4? Yeah, it must have been. I'll go pi on 2. Yeah. So we can see that the graph has been shifted across effectively. Our asymptotes have been shifted across effectively. Okay, so I just don't feel like I'm getting exactly the right number here, so I'll just go for minus pi on 4. That's better. Don't know what that was doing before. So we can see that pi on 2, the asymptote that was at pi on 2, is now at 3 pi on 4, an extra pi on 4 that way, because I made it negative, so it's shifting to the right. The center has gone from 0 to pi on 4, from pi to 5 pi on 4, and so on. So you're effectively shifting the whole graph, and that's what the phase shift does. And that's basically it for the transformations and how they apply. In terms of describing the transformations, if you're told to list them, exactly the same as you do for sine, cosine, in fact, any other function as well. You just list them in order. And you always make sure you take out the common factor. It is 11:24. So I'm going to stop the video there.